Okay, we'll go ahead and finish up section 10.4 here. We're talking about calculus with polar equations. We're on problem 9 of this worksheet. It says to find the area of the region common to the two regions bounded by the circle r equals -6 cosine theta and the cardioid r equals 2 minus 2 cosine theta. Okay, so if I set those equations equal to each other and then solve for theta, let me add 2 cosine theta to both sides and then divide by -4. -2 over 4 is -1/2. So when does cosine theta equal -1/2? Let's see. So when the adjacent side is a -1 and the hypotenuse is +2, so that'd be 2 pi over 3. And then if you flip the triangle down into quadrant 3, 4 pi over 3. Okay, but now when I look at this graph here, it looks like these curves intersect 3 times. Okay, I got once here at 2 pi over 3, once down here at 4 pi over 3, and then again right here at the pole, right? So now the reason why that third value didn't come up is because it's different coordinates depending on if you're looking at the circle or the cardioid. Okay, so I'm going to give my intersection points in terms of the circle here. So if theta is pi over 2, or is 2 pi over 3, cosine 2 pi over 3, that's -1/2 times -6, that's 3. Okay, so 3, 2 pi over 3, and then 3, 4 pi over 3. Those would be the intersection points. And then now if I'm doing this in terms of the circle, if theta is 0, let's see, cosine of 0 is 1, so r is -6. That's going to put me right here. Okay. If theta is pi over 2, now I'm going to use some symmetry. And remember with circles, you can completely draw out a circle on the interval 0 to pi. So that, and you can completely draw out a cardioid on the interval 0 to 2 pi. So that's why these have different coordinates here, is because the intervals are different. Well, if I look at half of the interval 0 to pi, so like if theta is pi over 2, cosine pi over 2 is 0, so r would be 0. Okay, so on the pi over 2 axis, I need to go at 0 units, and that's going to put me right there at the pole. And that's going to be the third intersection point. Okay, now I want to find the shaded area here, and I'm going to use some symmetry. If we, so by the way, I'm going to have to add 2 integrals. So let's see, the first integral is going to be where I'm going from pi over 2 to 2 pi over 3. Okay, and I find that little sliver of area there. Now, if I'm only working with that little sliver of area, I'm working with the circle. Okay. So I'm going from pi over 2 to 2 pi over 3, and integrate this the r squared, right? So talking about the circle there, -6 cosine theta, and then plus 1/2 times. Now the rest of this is going to be the cardioid there. So I'm picking up from 2 pi over 3, and I'm going to end at pi. And so I'll find that little sliver of area there. And then whatever this total area is of these two regions, this one and that other one there, I'll double that to get my total answer there. Okay, so I'm going to use some symmetry here. So I'm going to add 1/2 times the integral from going from 2 pi over 3 to pi of the cardioid, 2 minus 2 cosine theta. Okay. I'm squaring that. So, and then there's the 2 in front using symmetry. If I bring in the 2, 2 times 1/2 is 1, right? And -6 squared, that's 36. 36 is a constant. I can bring that outside the integral. This 1/2 is gone because it's times 2, right? And let me go ahead and FOIL this out. So 2 minus 2 cosine theta times 2 minus 2 cosine theta, that's 4 minus 8 cosine theta plus 4 cosine squared theta, d theta. And with cosine squared theta, I'm using the power reducing formula. We got 1/2 plus 1/2 cosine 2 theta. Okay, half of 36 is 18. And I'm going to use that again over here. Half of 4 is 2, right? Okay, and that will allow me to get the antiderivatives here of both these. Okay, so I got 18 times theta times sine of 2 theta divided by 2. Okay, and I'm going from pi over 2 to 2 pi over 3. And then it's going to be plus 4 theta minus 8 sine theta plus 2 theta plus the antiderivative of 2 cosine 2 theta would be sine 2 theta. Okay, and we're going from 2 pi over 3 to pi with that. So then when I plug in the bounds here, I plug in 2 pi over 3, sine of 4 pi over 3, that is negative root 3 over 2, okay? Times 1/2 is negative root 3 over 4, and then minus, when I plug in pi over 2, let's see, 18 times pi over 2, that's minus 9 pi. And then sine of 2 times pi over 2, that's sine pi, that's 0, right? Okay, plus, when I plug in pi here, then I'm going to have 4 pi and 2 pi, that's 6 pi, okay? And then minus 0 plus 0, okay? And then minus, when I plug in 2 pi over 3, I get 8 pi over 3 minus sine of 2 pi over 3, that's root 3 over 2, times negative 8, that's negative 4 root 3, okay? And then sine of 4 pi over 3, that's negative root 3 over 2, okay? Now when I simplify all of this here, I get 5 pi as the total area, okay? So that's the shaded area on this picture that I see. Okay, now there's a note at the bottom of this, which is really important, by the way. It says, to see the benefit of polar coordinates for the last example, consider finding the integral below, which gives a comparable area in rectangular coordinates. Now, I would hate to do either one of these two integrals. I don't even know how to do the first one. Okay, but so that's the point of like why we're looking at polar graphs and parametric curves, you know, is because sometimes when you integrate a problem or take a derivative or something, like it's way easier than it could have been if I stuck in rectangular coordinates. Okay, that's the point with this stuff. Okay. Now problem 10 is the last problem there. So we talk about arc length. It says let f be a function whose derivative is continuous on the interval alpha to beta. The length of the graph of r, which is a function of theta, from alpha to beta is given by this integral, okay, which is the same thing as this integral here. Now, as an example of that, suppose that we want to find the length of the cardioid, r equals 1 minus cosine theta on the interval 0 to 2 pi. Okay? So, let's see, I can completely draw out the curve on the interval 0 to 2 pi. I can completely draw it one time. So that's going to be the bounds on the integral here. And it's going to be the square root of r squared, and then plus dr d theta is the opposite of negative sine theta is sine theta. I'm squaring that, right? And then stick a d theta at the end, okay? When I FOIL this out, I got 1 minus 2 cosine theta plus cosine squared theta. Cosine squared theta plus sine squared theta is 1. Plus 1 is 2. So I'm looking at 2 minus 2 cosine theta underneath the radical there. If I factor out a 2, the square root of 2 is brought outside there. And left inside the integral, then I've got the square root of 1 minus cosine theta. Okay? So I'm right here right now. Okay? Now the next thing I'm going to do is I'm going to use this power formula for sine squared theta. That's 1/2 times 1 minus cosine 2 theta. Now, I don't have a cosine 2 theta, I got a cosine theta. So where I see, the 2 theta, I just I'll replace theta with 1/2 theta, because 2 times 1/2 theta, that's theta, right? And if I multiply both sides of this equation by 2, then 2 sine squared theta is equal to 1 minus cosine of 2 times theta over 2. The 2's are gone there, right? So 1 minus cosine theta, that's the same thing as 2 times sine squared theta over 2. Okay? And I split apart this radical here. I got root 2 times root 2, that's 2. And then now the square root of sine squared theta divided by 2, that is the absolute value of sine of theta divided by 2. Okay? Now if I look at a picture of that curve there, I got sine of x divided by 2, right? And if I look at the window, I'm going from 0 to 2 pi. And let me go from -2 to 2 on the y-axis there. Okay, and then if I hit graph, let's see, this is the entire curve on the interval of 0 to 2 pi for a sine of theta divided by 2. Now notice that this curve is entirely positive on that interval, right? So the point of that is to say that I don't need absolute value bars here because this curve is already non-negative, right? So I got 2 times the integral going from 0 to 2 pi of sine of theta divided by 2 d theta. And when I find the antiderivative there, that's going to be 2 times antiderivative of sine of theta over 2, that'd be negative cosine of theta over 2, and then you got to throw a 2 in front. So 2 times -2, that's -4. Then when I plug in my bounds, cosine of 2 pi divided by 2 is cosine pi, that's -1. Okay, and then minus, when I plug in 0, cosine of 0 is 1, and I'm subtracting 1, right? -1 minus 1 is -2, times -4 is 8. So the length of this curve here, to trace this out one time, I went 8 units, is what I'm saying there. Okay, so there's a couple of problems related to arc length in this section at the end of this section there. Primarily, a lot of the problems there in this section are going to be related to area. Okay, so that's very important for polar graphs there. The area and derivatives also. Okay. All right. So here's the homework. Take a look at those problems there when you get a chance. And we'll start in on chapter 11, which is the last section or last chapter for the course there. Okay.